All right, today we're doing a systems level analysis of a new AI architecture from Google. And the target is a really fundamental, reproducible bug that's inside every single LLM running today. Our goal here is to break down this defect, analyze the proposed architectural fix, and then, of course, review the performance data to see if it holds up. So here's the game plan. We're going to start by defining the core defect. Then we'll run a full root cause analysis on the current kind of flat architecture we all use. From there, we'll get into the paradigm shift that unlocks the solution, that's the hope architecture, before we validate it against the benchmarks and think about what this means for the long haul. Okay, first up, the Anterograde Amnesia defect. Let's talk about the input problem. Every large language model in production today has this built-in flaw that literally prevents it from forming new long-term memories. And let's be clear, this isn't a feature, it's a critical bug in the system design. So formally, this defect is classified as anterograde amnesia. In the clinical world, that's the inability to form new memories. For our systems, it means any information, any knowledge the model picks up inside its context window is just wiped the second the session ends. The state is never saved. And this architectural bug leads to some really concrete user-facing failures. You've probably felt this. Think about the coding loop. You spend a whole session teaching the model a new API, and the next day, gone. You have to start from scratch. Or the static assistant, which forgets something as critical as a user's peanut allergy the moment you open a new chat. I mean, this isn't just an inconvenience, it's a total failure of state management. So now, let's get into the root cause analysis. This memory failure isn't some surface-level bug you can just patch. The problem is actually baked right into the fundamental architecture of our current models. This slide really shows the core issue, this architectural mismatch. You know, biological systems like our brains, they process information on multiple frequencies. You've got fast waves for what's happening right now and slow waves for locking in memories. But our AI models, they use one single flat processing speed for absolutely everything. It's a huge design flaw when you think about it. So to put it simply, standard transformers force every single computation, whether it's processing one token or learning a complex idea, into the same single update frequency. The proposed solution here is to decompose the model, to break it down into nested computational loops that all operate at different speeds, which, sounds a lot more like that efficient biological design. And this brings us to the core technical insight of this whole new approach. It's a complete reframing of a component that we almost take for granted in the training process. So the paper asks this really central question, and it completely redefines the problem. It asks, what if the optimizer, the very algorithm we use to update the model's weights, isn't just a static math formula, but is actually a form of memory itself? Okay, first, let's just establish the baseline. This is the standard update equation for gradient descent with momentum. It's probably familiar to a lot of you. It's what dictates how the model's weights, W, get adjusted at each step based on the momentum, M. This simple linear rule has been the bedrock of deep learning for years. Now, the key insight here is how they recharacterize that momentum term, M. It's not just some velocity vector. It's actually a primitive memory system. It's basically a running average of all the past gradients. But because it's linear, it's an incredibly lossy compression. It's kind of like trying to understand a movie by just averaging all the pixels together into one big gray blur. Now contrast that with the new deep optimizer logic. The weight update is no longer this simple linear function. That momentum term, M, has been replaced by a learnable non-linear neural network. And this is the critical shift. The system isn't just learning from data anymore. It's dynamically learning how to learn. The optimizer itself becomes a trainable part of the model. And this diagram just perfectly illustrates the new system architecture. We're moving away from that flat, single-level view to this nested learning paradigm. Here, each level represents its own distinct optimization problem with its own dedicated gradient flow. And they're all operating at different frequencies. It's a total shift from a monolithic process to a hierarchical one. So this brings us to the concrete implementation of this nested learning idea. It's called HOPE, which stands for a Higher Order Processing Engine. This slide gives us a great side-by-side schematic of the architectures. So on the right, that's the standard, flat transformer you know and love. But on the left is HOPE. The first thing you'll probably notice is the feed-forward network, the FFN, is broken up into low, mid, and high-frequency layers. That's the core structural change right there. So really, the key architectural takeaway is this. We're moving from a single FFN layer with just one update frequency to a continuum memory system of FFNs, where each one has its own separate update frequency. And this is what allows the model to process information at different timescales, just like a biological system. Now, let's look at the update schedule, because this is wild. The fast weights, which handle immediate context, they update on every single token. Mid-weights update every 16 tokens. But get this, the slow weights, the model's core knowledge base, they only update once every million tokens. This is where you get these massive efficiency gains. The biggest part of the model is dormant in terms of writes 99.9999% of the time, which just slashes the computational burn rate. Okay, now for the performance review. I mean, the architecture is elegant for sure, but we need to validate its performance. So let's check out the benchmark outputs. And the results from the 1.3 billion parameter models are really clear. On perplexity, which is a measure of language understanding where lower is better, Hope scores a 15.11. That beats both the baseline Transformer++ and Google's own Titans model. And on complex reasoning, where higher is better, Hope again takes the lead with 42.52% accuracy. This chart just visualizes that key reasoning metric. You can see Hope establishing a new state-of-the-art on this benchmark. And this really demonstrates that the multi-frequency architecture doesn't just make things more efficient, it actually improves the core reasoning capability of the model. Finally, let's zoom out and analyze the long-term system implications. I mean, what does a shift in architecture like this really enable down the road? So here are the primary system upgrades you get. First, and most obviously, it directly fixes that anterograde amnesia defect by enabling true memory consolidation. Second, because the optimizer is now its own neural network, the model can literally modify its own learning rules. This means we're moving away from static, compiled code toward dynamic, evolving systems that just feel much more aligned with the physics of actual biological intelligence. You know, this whole architectural philosophy really echoes a recent statement from NVIDIA's Jensen Huang. He argued that the next major breakthrough wasn't going to come from computer science, but from the physical sciences. Well, this paper provides a concrete mathematical framework for that exact idea. And this really leaves us with a final, provocative question for all the system architects out there. By building models with these nested loops that can learn how to learn, are we no longer just writing code, but maybe engaging in a new kind of computational biology? That's the massive paradigm shift this work is suggesting.